On a clear night, far from light pollution, you might see a few thousand stars. They appear to be small, still, and peaceful, but they are none of those things. Consider the brightness and heat of the midday sun, and you are presented with a much clearer picture of what a star truly is. The universe consists of mostly hydrogen, some helium, and trace amounts of heavier elements. Stars are made from this material and share its composition. While it's common to describe a star as a hot ball of gas, its core temperature is incredibly high, typically millions of Kelvin, making much of the gas a plasma. Plasma is the fourth state of matter, and it forms when gas has been heated to such an extent that it becomes ionized, meaning it's stripped of its electrons. These electrons then float within the plasma, along with the positively charged ions they were formerly bound to. This makes it highly electrically conductive and magnetically active. A star's core sustains a continuous fusion reaction where the energy produced counteracts gravity's pull and prevents its collapse. Fusion is an incredibly efficient process, converting mass into energy. As lighter elements fuse into heavier ones, a minuscule amount of mass is consumed to generate immense energy. Einstein's famous equation, E equals mc squared, illustrates this principle. Here, E represents energy, m mass, and c is the speed of light, approximately 300,000 kilometers per second. This large value of c demonstrates that even a small mass is equivalent to vast amounts of energy. In a typical star's core, the temperature reaches millions of degrees Kelvin and the pressure reaches millions of gigapascal. These conditions force hydrogens so close together that they very occasionally overcome their electrostatic repulsion due to their shared electric charge. Even at these temperatures, a hydrogen nucleus, which is just a proton, can bounce around in the star's core for billions of years before that happens. Once it does, the strong nuclear force takes over and the two nuclei fuse to form a deuterium nucleus, releasing a positron and neutrino in the process. The deuteron, as they are known, doesn't last long. Deuterium is a heavier isotope of hydrogen and is used in prototype fusion reactors on Earth for this reason. It fuses much more easily than vanilla hydrogen. In about a second, it fuses with another proton, releasing a gamma ray and forming helium-3, a light isotope of helium-4. The helium-3 nucleus fares better than the deuteron and can bounce around for a few centuries before it too fuses with another helium-3 nucleus to form beryllium-6, which is very unstable and immediately releases two protons to become helium-4. This process is called the proton-proton chain, and it is the primary fusion pathway for most stars. Each one of these reactions releases energy. As a new particle is formed, it is endowed with kinetic energy from the reaction, which is released into the star as heat. When a neutrino is formed, it escapes the sun, taking a small amount of energy with it. Neutrinos don't interact with the strong or electromagnetic forces, so they tend to fly through matter unimpeded. In the last second, 100 trillion solar neutrinos pass through your body. These neutrinos spawned in the sun's core 8.5 minutes ago. When a positron is emitted, it typically annihilates with an electron to produce gamma rays. Positrons, also known as anti-electrons, are a form of antimatter and thus annihilate with matter on contact. They are attracted to electrons specifically due to having the opposite electric charge. When gamma ray photons are created, they scatter off other particles in the sun's core for hundreds of millennia in a random dance that eventually leads to their freedom. Gamma rays are the most energetic form of electromagnetic radiation. The process of scattering results in them slowly losing that energy as they deposit it into the sun as heat. By the time they escape, the photons are typically in the infrared or visible light range with a small portion in the ultraviolet range. Once liberated from their stellar confines, some of these photons race towards Earth at the speed of light, taking approximately 8 minutes to reach us. Consider this: the sunlight that nourishes your plants and warms your face originated in the sun's nuclear furnace hundreds of thousands of years ago, during the evolution of our species, Homo sapiens. Only the smallest stars are fully convective, meaning that as stellar matter in their center heats up, it then rises to the surface before cooling and sinking back down again. Stars like our Sun have a few distinct regions in their interior. There's a core, the innermost quarter of the star, at 15 million Kelvin in temperature. This temperature and pressure are enough to sustain hydrogen fusion. Then there's the radiative zone from 25 to 70% of the distance to the surface, and falling from 7 to 2 million Kelvin. This is where the photons generated from fusion in the core bounce around and very, very slowly make their way outwards. And there's a convective zone, which is about 200,000 kilometers deep and extends almost to the surface, with the temperature falling from 2 million to 5,700 Kelvin. You might notice that this last value corresponds to LED light bulbs marketed as daylight white. At these temperatures, solar material is less ionized and is thus more opaque. This opacity dramatically slows radiative transfer, and convection takes over as the main mechanism. This causes hot areas to rise and cool areas to sink. This is visible from the surface of the star in what is called solar granulation. Once photons get to this layer, their escape is imminent. After this, we reach the stellar atmosphere, which comprises several distinct regions, including the photosphere, the chromosphere, and the corona. As we ascend from the core, temperatures have steadily decreased, but surprisingly this trend now reverses. Reaching 20,000 Kelvin in the chromosphere and 1 million in the corona, scientists are still investigating the reasons behind this phenomenon. Stars continuously shed a small amount of their material in what we call the solar wind. This plasma is composed of protons, electrons, and helium nuclei and streams out from the star at 400 kilometers per second. Have you ever looked at a picture of a comet and noticed that its tail is pointed away from the sun? This is because the solar wind is peppering the comet and vaporizing some of its surface, which forms the tail. The effect is stronger the closer the comet is to the sun, since that is where the solar wind is most dense. The solar wind is mostly blocked by Earth's magnetic field. During bursts of more energetic space weather, like coronal mass ejections, some of the stellar material is funneled into the north and south poles and collides with the Earth's upper atmosphere. This causes the sky to glow red, green, and purple, and is known as aurora borealis, or northern lights, and is beautiful to watch if you ever get the chance. In our galaxy, the Milky Way, there are roughly 200 billion stars. And there are at least 2 trillion galaxies in the observable universe, each with a similar number of stars, which means there are at least 400 sextillion stars out there. Most of these stars reside in the system of more than one star, making our Sun a minority. Binary systems are very common, but systems with up to 7 stars have been observed. The closest star system to Earth, Alpha Centauri, is 4.3 light-years away, and it hosts 3 stars. There is a dizzying array of stars in the sky, so astronomers have developed ways to classify them. The most common tool for this is called the Hertzsprung-Russell diagram, which plots stars by spectral type and temperature horizontally and luminosity vertically. For most stars, there is a somewhat linear relationship between their luminosity and temperature, and this is shown on the diagram as a somewhat diagonal cluster, rising from the bottom right to the top left in what astronomers call the main sequence. Note that the horizontal axis is reversed here. The letters used to denote the spectral class are in an order that doesn't make much sense today, just consider it legacy astronomical baggage. 90% of the stars are in the main sequence, so we will start with those. Red dwarfs are the smallest, faintest, most numerous, and longest-lived of all main sequence stars. Many are expected to keep fusing hydrogen for trillions of years, much longer than our Sun's 10 billion. They make up for 3/4 of main sequence stars and are typically less than half as massive as our Sun. They are so dim that none are visible to the naked eye from Earth, even though our closest star, Proxima Centauri, is a red dwarf. These are stars like our Sun, weighing between 1/2 and 1.4 solar masses, appearing white to yellow to orange in color, and making up about 1/4 of main sequence stars. They fuse hydrogen on the main sequence for billions to tens of billions of years. Alpha Centauri A and B are 2 such stars, being G and K class respectively. And of course, our Sun is a G-class star. These massive blue and bluish-white stars account for less than 1% of main sequence stars, yet they account for the majority which are visible to the naked eye. Their high mass results in such a crushing force in their cores that they burn through their nuclear fuel much more quickly than lighter stars. The most massive ones leave the main sequence after just a few million years. Sirius A and Rigel are 2 such stars, being A and B class respectively. Once main sequence stars run out of hydrogen in their cores, they undergo a transformation into much larger and more luminous stars and often change in color. Our Sun will become a red giant when it gets to this stage. Betelgeuse is a red supergiant that evolved from a much larger O-type star. All but the most massive stars will turn into white dwarfs once they are no longer able to sustain fusion. They are small, typically Earth-sized, dense, a teaspoon weighs a few tons, and very hot with a surface temperature of up to 100,000 Kelvin. As remnants of stellar cores, they are mainly composed of helium, carbon, and oxygen. They are saved from collapse by electron degeneracy pressure, which is a powerful force that prevents more than one electron from occupying the same quantum state. Most stars begin their life in a molecular cloud, often referred to as a stellar nursery. These clouds of gas and dust are huge, sometimes spanning hundreds of light years, and very cold, maybe 10 or 20 Kelvin. Although they are very sparse, clumps sometimes form and grow massive enough to start forming a protostar. As the clump collapses into a protostar, the small amount of initial spin from the environment grows due to the law of conservation of angular momentum. It soon forms a disk shape which will eventually spawn planets, moons, comets, and asteroids. If the protostar is supplied with enough mass to sustain hydrogen fusion in its core, it graduates to a full star and joins its brethren on the main sequence. This process takes 500,000 years or so. Ultraviolet radiation and stellar wind from the newborn star will expand outwards to blow and sculpt the surrounding material. This will compress it and trigger more clumps to collapse, leading to more star formation. If any massive stars in the cloud end their lives as a supernova, they will release huge amounts of energy into the cloud, along with heavier elements, further spurring star formation in the surrounding regions. This feedback loop accelerates the rate of star birth and simultaneously disperses the molecular cloud. As a star fuses hydrogen into helium, that helium will accumulate in the core, which causes its density and temperature to increase. This speeds up the rate of fusion, so the star becomes hotter and more luminous as it ages. It will also lose about 0.7% of its mass through nuclear fusion by the time it leaves the main sequence. Our Sun is about halfway through fusing the hydrogen in its core into helium. Once the hydrogen in the core runs out, the star begins to fuse helium, and the additional heat causes hydrogen outside the core to start fusing too. This dramatic increase in energy release marks the beginning of the end for the star. It puffs up to 200 times its former size, becomes 2,000 times more luminous, and also redder. A low-mass star like a small red dwarf stops fusing hydrogen after a few trillion years and becomes a white dwarf made of mostly helium. Sun-like stars will also end up as white dwarfs after becoming red giants, but having fused their helium, they will be made of carbon and oxygen. In their death throes, they will undergo a period of instability and eject much of their mass into the space around them, seeding the surrounding area with heavier elements. The newly formed white dwarf ionizes this material with its ultraviolet radiation, which causes a dazzling display of rich colors. This results in the formation of what is known as a planetary nebula, although it has nothing to do with planets. That's just more astronomical legacy baggage. These are some of the most beautiful objects in the sky and can take a wide variety of forms. The Ring and Cat's Eye Nebula are popular examples. White dwarfs slowly cool and fade over billions of years to eventually become black dwarfs. The largest stars will die spectacularly. After their supergiant phase, stars that had more than 10 times the mass of the Sun collapse into either a neutron star or a black hole. The remnant of the star must possess at least 1.4 solar masses, known as the Chandrasekhar limit, to overcome electron degeneracy pressure. It then collapses into a neutron star, which is itself prevented from collapsing further by neutron degeneracy pressure. If the initial star was greater than 40 solar masses, its remnant will typically have at least 3 solar masses, which is enough to overcome even neutron degeneracy pressure and collapse into a black hole. The collapse into a neutron star or black hole is accompanied by a supernova, one of the most luminous events in the universe. This seeds the surrounding gases with heavier elements from the dead star, encouraging star formation and also making more complex things like life possible. Supernova 1987A was discovered that year in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way, 160,000 light-years away. This is notable because the event was relatively nearby, but more importantly, astronomers had been observing the star in the years leading up to its demise, which provided them with insight into stellar evolution and death. There is strong evidence for microbial life on Earth 3.5 billion years ago, about 1 billion years after the Earth had formed. There is weaker evidence for life as far back as 4 billion years ago, possibly even earlier. Earth was an extremely hot and violent world in its first few 100 million years, so life evolved on Earth very quickly. This fact is often used to argue for a universe that is teeming with life, but since we've only got a data set of 1, it's difficult to make that determination. There are a few universal requirements for life. A source of energy, typically coming from a star, and the heat from the host planet. Sometimes it's from chemistry. Diversity of elements to support biochemistry. All life on Earth requires carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Additional elements like the iron in your blood are also used. A solvent to facilitate the above chemical reactions. Water is good for this purpose since it remains liquid through a very broad range of temperatures and is hot enough at those temperatures not to inhibit chemistry. Stability. Although life took only a few 100 million years to form on Earth, complex multicellular life took 4 billion and intelligent life 4.5. So we can exclude the most massive stars since they just don't last long enough. Probably. Aside from these requirements, there are many other factors that are thought to be favorable to life, but it's not understood how critical they are. Plate tectonics, which allows for the recycling of carbon and helps us regulate the climate. A magnetic field, which shields against radiation and space weather, protecting the atmosphere from being eroded away. A moon, which helps stabilize a planet's axial tilt. Although astronomers have learned much about nearby stars and a little about nearby planets, we don't have enough data yet to provide any sort of reasonable estimate for how common life is. We know that there are about 200 billion stars in the Milky Way and that there are at least that many planets, probably many more, but we have only detected a few thousand at the time of this video. Since these planets are so small, distant, and dim, we are rarely able to image them directly. Rather, their existence is inferred based on their host star's wobble or periodic dimming. Both of these methods have significant limitations, and any measurements from them typically contain large error bars. Additionally, our findings are skewed towards larger planets around smaller stars. Still, more and more planets are being detected every year, and our instruments and techniques are improving, so it's very possible that we will find signs of life on an exoplanet within your lifetime. Within the next billion years, our sun will have become hot enough to boil off the Earth's oceans and cause a runaway greenhouse effect, rendering it uninhabitable to complex life. As it heats and grows further on its way to becoming a red giant, the Earth will be heated to the point of losing its atmosphere and then melting its crust before finally being swallowed up by the very thing that sustained the life it harbored. The Earth will fall into the sun and become part of the white dwarf that is left behind. Since very large stars don't live long lives, it stands to reason that smaller stars are good candidates to look for planets with life. The smallest stars, red dwarfs, are plentiful and long-lived, but they also have some drawbacks. First, because of their small mass, their habitable zone, where water can exist in liquid form, is both small and very near the star. Planets that are close to the star tend to become tidally locked, which means that the same side faces the star at all times. Our moon is tidally locked to the Earth. For these planets, one side would be scorching hot and the other would be freezing cold. The proximity would also mean that solar flaring could strip the atmosphere from the planet over time. And red dwarfs are known to be very active stars with lots of flare activity. Finally, they are highly variable, with large swings in luminosity that would be challenging for life to deal with. So it seems that the best places to look for life will be around sun-like stars or ones a little less massive. Thanks so much for watching my video. If you liked what you saw, consider liking and subscribing and leave a comment below.